Okay, welcome back. This is going to be part 2 of the machine learning basics portion of this course. Where we're covering different linear regression, logistic regression, and how these different algorithms work. And in this one, we're going to talk about optimization, primarily about gradient descent. So if you've ever heard the term gradient descent, we're going to talk about that and how that works here. And most machine learning algorithms are trained, or their model parameters are trained, using some variant of gradient descent. So we'll talk about that as a basic core concept of machine learning in this video. So I'm going to pull up the PowerPoint, and here we go. So again, this is part 2, and we just got done talking about linear regression and optimization. Yes, and here's the slide to prove it. So where we left off with this last part, and if you look up above, we were talking about how do you choose these different machine learning parameters. We talked about this cost function here described as J, as a metric that evaluates kind of the quality of your algorithm to capture the actual outputs. And now we're going to talk about, an automated method to select these different model parameters. But I thought I'd start off first with let's go to a simple example and kind of walk through in Excel one of these examples with a number of different inputs and output response and how you set up this algorithm and how Excel actually approaches doing the optimization. Yes, why Excel? And I used to say because most people know Excel. Certainly a lot more people know Excel than they know Python and MATLAB and all these other different programming languages. While I do cover some of that in this course, just to kind of throw out there Python scripts so you can see really how easy it is, to tackle some of these and integrate some of these concepts within a programming language. I opted not to go down this route just because there's a lot of videos out there that tackle this using MATLAB or Python. Not too many that use something like Excel to really unpack how these algorithms work. So here's linear regression. We just got done covering it, and this is a video that's going to show us walk through, make the prediction, compute the L2 loss function, garner the or calculate the cost function here, and then use optimization to actually solve for these different model parameters, these theta parameters. When I talked about the direct solve, here's the values that should come up after we get done with optimization. Here's the actual values off to the side. You can see that we've taken thickness, which is one input, and then computed the V50, this metric that evaluates the effectiveness of a bullet or armor. And here's all the actual values that are on there. Of course, our model is predicting 0 at the moment, or is not even predicting anything. So the model is not on the screen right now. So let's go ahead, turn off laser pointer. I'm going to go ahead and start this video, and then I'm going to talk through it as we go along. Actually, another thing to mention is you can see the thickness, hardness, obliquity values here. These have been normalized so that they're a mean of 0 and a standard deviation of 1. So in that respect, when we compute theta 1, 2, and 3, and sometimes I do that normalization, you can compare them to see which of these different features is, the output is most sensitive to. You can already see the answers here. So it's theta 1, which is this thickness of the armor, is the most influential on the V50 metric. And we'll show how we get those values using Excel's optimization. Okay, I'm going to turn back on laser pointer. You see you have to initialize your theta somewhere. Here we're going to name the variable, which we've covered in other videos. Now our prediction, mmult, so that matrix multiplication. We're going to choose all of this. So you can see it's a dynamic array because it added the hashtag. You can type in theta since we've named these thetas as that theta variable. It fills in a dynamic array of all zeros. So it's predicting 0 because these model parameters are all 0. And here we have y minus y hat squared. So these loss function values are very high because the actual values are way up in the 6 to 900s. The predictions are at 0. We pulled up solver. You're going to set the objective to the cost function, and you want to obtain that by changing these model parameters. So again, this is similar to what we've shown in other videos. You can press solve, and it's actually going to use something similar to gradient descent to actually come up with these values. So we're going to keep this solution. And what I want you to observe here, so we've got now this model with these model parameters. We've used optimization to obtain these. Again, initially it was at 0. If you would compare these ones that we did with this optimization process to the direct solve, you're coming up with the exact same values, so that's a good thing. Now if you look at the line, one thing you may notice is that it's not a straight line. What's actually happening is that in predicting these actual values, you also have hardness and obliquity. So there's really like a three-dimensional problem here. So when it looks like this line is like curving, it's because these values are in and out of the page, so to speak, because of these other dimensions. So, we're trying to, show the prediction of three-dimensional data on a one-dimensional plot or along this one dimension of thickness. So that's why it looks that way. And this direct solve, you might say, well, geez, why don't we do that all the time? And I'll talk a little bit about that in this section. But again, this goes back to the linear algebra. We can solve directly for these model parameters using X transpose, X, and Y. And here's the function down below. It looks kind of hairy, but there's multiple matrix multiplication. You can see this matrix inverse is that first term, which is a matrix multiplication of the transpose of X times X. So you need to do that first. Then you invert it. Then you matrix multiply that by X transpose. And then you matrix multiply that by Y. And that gives you those model parameters that we showed in just the last screen. So yeah, how do you optimize these parameters? How does this all work? And yeah, I just showed how, we can use this formula, this linear algebra to rearrange these different variables in order to directly solve for that. But you may also notice, this -1, this is an inverse of this matrix, after you multiply these two. And you can't always just invert a matrix. When you think of the sheer size of all these data sets in terms of the number of rows or observations and the number of factors, it gets unwieldy at some point, and computationally it's just very difficult to do that. Also later, when we're talking about variance, bias trade-offs, and hyperparameters and regularization, that makes it even more difficult to use this method. And so it really doesn't work in a lot of cases. So what is optimization? We're going to iteratively solve an objective function. We talked about this cost function by changing a set of parameters. So changing these model parameters, which are modifying our inputs, to achieve kind of that good prediction. So I actually took the data here, and this is what the cost function looks like, is a center plot as a function of theta naught and theta 1. So you have kind of this valley here, right? So if you think of this as a hill that starts and goes down into a valley and then goes back up, if you think about kind of the topology of this, this is our optimal model, is this gold star. And you may start from the blue star or the green star in order to get to this optimal model. So I've shown in the lower left-hand side and lower right-hand side, if you think back to, as we change just one of these model parameters, how does that affect the cost function? You can see here that the blue and green are much higher than the optimal model. And so we want some technique that's actually going to drive it down in an automated way to this gold star. And how do you do that? You do that with gradient descent. So how you read this equation is it's going to take the model parameters and it's going to update them. And how is it going to update them at each of these different steps? Well, it's going to take the current set of model parameters. It's going to subtract alpha times this derivative term. So this derivative term, is the cost function and how it's changing with respect to each of these different model parameters. And I'll go into that a little bit more of why it looks like that in the next slides. So how do you optimize these parameters? So we're going to use gradient descent, and we're going to talk through the different terms and what they do. First is this slope term, or this derivative term. So we're taking the cost function, which as you're computing the cost function, remember you have to compute a prediction, and that prediction requires theta naught and theta 1. And then you have to compare that prediction with the actual value to come up with the loss functions. And then the average of those is your cost function. So this cost function is actually a function of theta naught and theta 1 of your model parameters. And you want to take the derivative of that or understand how that changes with respect to each of those model parameters. So here I put J. You could replace J with 0. And this whole equation, describes how you should change theta naught. You can change J to 1. And that would, this whole equation, if you change J to 1, would describe how theta 1 changes. Okay, so that's the slope. So if you look at this blue star and the slope, it's in that sort of, it's the rise over run at that particular point. The second thing I want you to observe is we have this negative sign. So why not just add these terms, and why do you subtract them? I mean, the positive, if you were to add it, then this is going to go in this opposite direction. It's going to increase, and you can see that your cost function is going to increase with that. So what you want to do is you want to drive it in this negative direction. So in order to move towards what is the lower cost function, you want a negative sign there. And the last is this hyperparameter alpha. So this is really the size of the steps. So if you start here at the blue star, you now know the slope and you know the direction, but you don't know how far you should go. And so that's where alpha comes into play. Alpha is going to tell you if you want to step in small increments, as you go towards this optimal value, or very large increments. Now, the nice thing is if you choose it small enough, you're always going to kind of iteratively move towards this optimal value. If you choose a step size that's too large, you can get in a situation where it can jump past it and then jump past it again and jump past it again. So you do want to take care in selecting these hyperparameters such that you're actually going to obtain an optimal value. And now, this alpha term, it's often called the learning rate within gradient descent. It is a hyperparameter. So how do you think about, what does hyperparameter even mean? Well, once you've trained your model, you really only need these model parameters in order to make a prediction. You don't need this hyperparameter to show up anywhere. So it's a parameter that affects the training process, but it doesn't show up when you actually later go to implement your model and to make predictions. So that's how you can think of these hyperparameters, as they don't actually need to go into the model, but they do affect how the model is trained. This is a 4-minute video, so it's a little long, and actually if I were to go back, I'd probably change a few things here and there, but I did want to kind of show how these algorithms work. So again, what you have here, and I'm going to try to narrate as this video plays, but we have our different theta values up at the top. So, and this is after we scale them and what the values are. At some point, this linear algebra or direct solve will probably show up as well. We have 3 input variables, so thickness, hardness, obliquity. We have the actual value here. So this is the problem that we've actually been doing all along. The first step of all this was to normalize it. So we've actually computed the mean and the standard deviation of these columns, and we'll show how we actually scale these inputs in a way so that we can, act upon these normalized values as opposed to the original values. And again, either way will work in terms of implementing the algorithm and making the prediction. The nice thing about normalizing these different features is that then these theta values, you can compare them directly to actually see, okay, moving an increment for thickness or hardness or obliquity will actually have this much effect on our prediction or our output. Okay. So with that, I'm going to go ahead and start and narrate as we go. Okay, you need to first initialize these variables. For standard scaling, again, you can select the column here. And what you want to do is you want to subtract the mean. So that sets the mean to 0. You want to divide by the standard deviation, and that sets the standard deviation to 1. So we've normalized all of these columns to a mean of 0 and a standard deviation of 1. Now we want to make a prediction. So here's matrix multiplication. Again, we're going to select all of our x's, comma, and then select our theta values. Because this is regression, we're now going to use the L2 loss function. It looks like here I've actually use the let function. So again, the let function is you define a variable and then you define what that variable is. So here y hat is this dynamic array here. Mean squared error, so our loss function is going to be y minus y hat squared. So again, the nice thing with the let function is you can see and name variables very easily. Here we've actually computed the derivatives, for each of these model parameters. So we're once again going to use the let function to actually, craft what the values are here. Here's xs, so that would be our x's after scaling. So we've named y hat our x's. And then the derivative for this, -2 times y minus y hat times xs. And then you're going to output dj. So there we go. That's actually giving us all of our derivatives. So that's a derivative term within this function. Here, just to make it easier, we're going to transpose our theta up above. Again, we're going to take the average of these thetas. So each of these is a derivative with respect to x0, x1, x2, x3. So that's that derivative term for each of those. There's our alpha term. I'm actually going to go back because this goes rather quickly. Okay, so that was the average. There's the alpha term, which corresponds to the alpha term in that gradient descent. Here's where you actually have to go in and modify it so that you can manually iterate things. So I wanted to show in an iterative fashion how it steps through and does gradient descent. So what I've done is I've set up kind of a recursive algorithm. It's computed all of these things. And now what it's actually doing is going back to this x scaling. It's going to transpose these. It's going to subtract alpha multiplied by, again, these derivatives. So there's after one iteration. And then you can, continue iterating on this. So now it's iterating. You can see what the direct solve is, and we're continuing to iterate. It's driving that cost function lower and lower. You can see it becomes more and more difficult as you go along, or it's moving just, smaller and smaller increments in order to finally obtain the minimum cost function. So that's how you actually set all this up within, a computing platform like Python, or what's going on behind the scenes when you're doing optimization. So with that, here's just a question to kind of test people on, have they got an understanding of some of the different concepts that were presented here. So the following equation has all of these except, so y is equal to a function of x and theta. So which one of these is not, within this whole function? And so you can take a second, read through the different options, and try to understand, okay, well, which of these is not represented when it comes to making a new prediction? Yeah, and so again, our inputs are our x's, outputs are y, the model parameters are theta, the machine learning algorithm itself is this function. And what doesn't show up, though, is a loss function. So once you've optimized everything, you now have the optimal model parameters. You have your machine learning algorithm, obviously. You've used your training input and outputs. Now, all you really need is new inputs in order to make a prediction. So the loss function is, in essence, a choice. It's kind of like a hyperparameter, so to speak. It's a choice. It doesn't reflect the final model and how it makes predictions, or isn't reflected in the final model. And the alpha term is nowhere in here either. Okay, so with that, we've kind of covered optimization, gradient descent, and in the next video, we're going to lean into logistic regression. So an algorithm that is typically used for classification, and what does that look like? Okay, so thank you, and again, we're going to cover logistic regression, which has a new loss function, that we'll cover in this next section.